Vibration analysis, causes of unbalance in rotating machinery, factors leading to instability in mechanical rotation. Introduction to rotating machinery unbalance, why unbalance is a critical reliability issue. Unbalance in rotating machinery refers to a condition where the mass distribution of a rotating component is not symmetrical about its axis of rotation. When such a rotor operates, centrifugal forces are generated due to this uneven mass distribution. These forces act radially outward and increase proportionally with the square of the rotational speed, which makes unbalance especially critical in high-speed machinery. Even a small mass deviation can generate significant dynamic forces that are transmitted to bearings, shafts, and supporting structures. Over time, these forces lead to elevated vibration levels, accelerated wear, and eventual mechanical failure. Understanding unbalance is fundamental in the fields of maintenance, reliability engineering, and vibration analysis because it is one of the most common and easily detectable causes of machine vibration. From electric motors and pumps to fans, compressors, and turbines, unbalance affects nearly all forms of rotating equipment. Recognizing its characteristics allows engineers to diagnose problems accurately and apply corrective actions such as balancing, alignment, or component replacement before severe damage occurs. Unbalance is considered a critical reliability issue because it directly impacts machine health, operational stability, and safety. Persistent unbalance causes continuous vibration at running speed, which accelerates fatigue in rotating and stationary components. Bearings and seals are often the first components to suffer, leading to lubrication breakdown, overheating, and leakage. Shafts may experience cyclic bending stress, increasing the risk of cracks or catastrophic failure. Additionally, unbalance reduces machine efficiency by increasing frictional losses and energy consumption. From an operational perspective, unbalanced machines require more frequent maintenance interventions, higher spare parts consumption, and increased downtime. In severe cases, unbalance can result in excessive noise, structural damage, or even safety hazards for personnel. For these reasons, unbalance is treated as a primary fault condition in predictive maintenance programs and is typically one of the first issues investigated during vibration analysis. Classification of unbalance, manufacturing-related causes of unbalance. Unbalance in rotating machinery is commonly classified into three main types: static, couple, and dynamic unbalance. Static unbalance occurs when the mass centerline is offset from the shaft centerline, causing the rotor to settle with a heavy spot at the bottom when stationary. Couple unbalance arises when two equal unbalanced masses are positioned at opposite ends of the rotor, creating a rotating moment without a net static force. Dynamic unbalance is the most common condition encountered in real machines and represents a combination of static and couple unbalance. Each type of unbalance produces distinct vibration characteristics and requires specific balancing techniques. Understanding these classifications is essential for selecting the correct balancing approach, whether single-plane or two-plane balancing. Failure to identify the correct type may result in ineffective corrections and persistent vibration problems. Manufacturing processes are a common source of initial unbalance in rotating components. Casting and forging imperfections can introduce uneven mass distribution due to porosity, inclusions, or inconsistent material flow. Variations in material density, even within the same component, may lead to residual unbalance after machining. Machining inaccuracies such as uneven material removal, off-center drilling, or dimensional tolerances further contribute to the problem. Although many rotors are balanced at the factory, residual unbalance may still remain within acceptable limits. However, when operating conditions change or components are modified, this residual unbalance can become significant. Understanding manufacturing-related causes helps engineers distinguish between inherent design limitations and faults introduced later during operation or maintenance. Assembly and installation causes, operational and maintenance-induced unbalance. Improper assembly and installation practices are frequent contributors to machine unbalance. Misalignment between coupled components can distort rotating elements, effectively shifting the mass distribution. Poor fits between shafts and hubs, such as excessive clearances or uneven interference fits, may cause eccentric rotation. Uneven tightening of bolts or mounting hardware can also distort rotors or attached components like impellers and couplings. In many cases, machines that were balanced correctly at the factory develop unbalance after installation due to these issues. This highlights the importance of precision during assembly, adherence to torque specifications, and verification checks such as run-out measurements before commissioning equipment. During normal operation, machines are exposed to conditions that gradually alter mass distribution. Material buildup from dust, product residue, or scale is common in fans, blowers, and mixers. Corrosion and erosion remove material unevenly, particularly in pumps and turbines handling aggressive fluids. Where deformation or thermal distortion can further contribute to unbalance over time. Maintenance activities may also introduce unbalance if components are replaced, repaired, or modified without subsequent rebalancing. Examples include replacing impellers, welding repairs, or inaccurate field balancing. These factors make unbalance a dynamic condition that can develop even in well-maintained systems, emphasizing the need for continuous condition monitoring. Symptoms and detection of unbalance, impact on safety and key takeaways. From a diagnostic standpoint, unbalance produces characteristic vibration patterns that are well understood in vibration analysis. The most common symptom is dominant vibration at 1 times running speed, 1 times RPM, primarily in the radial direction. Phase readings are typically stable and consistent, which helps differentiate unbalance from other faults such as misalignment or looseness. As speed increases, vibration amplitude rises significantly, reflecting the centrifugal nature of unbalance forces. These predictable symptoms make unbalance one of the easiest faults to detect using vibration monitoring tools. Early detection allows corrective balancing to be performed before secondary damage occurs. The impact of unbalance extends beyond mechanical wear to include safety, cost, and operational reliability. Excessive vibration can lead to structural damage, fastener loosening, and increased noise levels. In high-speed machinery, unbalanced forces can become severe enough to cause catastrophic failure, posing risks to personnel and surrounding equipment. From a business perspective, unbalance increases maintenance costs, energy consumption, and unplanned downtime. The key takeaway is that unbalance is a fundamental but manageable condition. By understanding its causes, recognizing its symptoms, and applying proper balancing techniques, organizations can significantly improve machine reliability, extend equipment life, and enhance overall operational safety.